In this video, we are going to be talking about the first law of thermodynamics. And the first law tells us that the internal energy of an isolated system is a constant. This is also called the law of conservation of energy. And the cute version of that law is that energy is neither created nor destroyed. So if you have some total system consisting of your system and its surroundings, the change in internal energy of the total system is always zero. You can relate the change in the system's internal energy to the change in the surroundings' internal energy via this relationship here, where we see that any energy gained by the surroundings is lost from the system and vice versa. A corollary to the first law is that heat and work are the only two ways in which you can change the internal energy of the system. So we can take the delta U for the system and write it as a sum of heat and work. This is the finite change version of the first law, and here is an infinitesimal version of the first law, where we have the exact differential for the internal energy. It's a combination of the inexact differentials for heat and work. You can also write similar equations for the surroundings. One thing to keep in mind, though, is that the heat from the surroundings perspective is the opposite of the heat for the system. So any energy transferred from the surroundings to the system via heat is going to have the opposite sign. The same thing goes for work as well. In this problem, we are being asked to use the first law, and it's a pretty straightforward problem. So what we have here is some electric motor that produces 15 kilojoules of energy as work, and it loses 2 kilojoules of energy as heat. So to calculate the change in the internal energy, we would write delta U equals Q plus W. In this case, the heat is 2 kilojoules, and that is going to have a negative sign due to the fact that the system is losing that energy. And then the sign for the work is also going to be negative because the motor does work on the surroundings. So we get minus 17 kilojoules for the delta U for this problem. I'll leave the part B as an example for you to try yourselves. Again, it's going to use this formula, and then what you have to do is figure out is the number for the work positive or is it negative? Same thing for the heat. And so this is practicing your sign conventions for heat and work. I'll move on to the next subtopic here. We are going to be focusing on doing some work calculations, and in particular we're going to be focusing on a special type of work called pressure volume work that involves the expansion or compression of a gas against some external pressure. Here is the sort of physics version of the definition of work. Okay, so you're essentially moving an object through some distance where it's exposed to a force of some sort. So this is the definition of work. If you take these two terms here and you multiply and divide by a surface area, you wind up with this expression here, where the force over the area can be defined as the external pressure, and then the area times this infinitesimal distance can be viewed as a change in volume. Here I have a figure representing that. So the idea is we've got some sort of piston, we've got a gas inside the piston has a particular surface area. Let's say the pressure inside the gas is a little bit larger than the external pressure, And what you're going to find is that the piston is going to expand in volume, okay, and there's a certain amount of work associated with that. And then here is the formal definition for calculating that work. It's minus the external pressure times the volume change. The purpose of the minus sign is to make sure that we follow our sign conventions for work. When the volume gets larger, that means that the gas is doing work on the surroundings, and so the system is losing energy, so we need to have a negative sign to indicate that that work would be negative. Conversely, if the surroundings was doing work on the systems, then we would have a negative volume change. That negative times the negative would give us a positive work, meaning that the system would gain energy via that work. Okay, so the sign is important. This is our definition. In general, the external pressure can be a function of the volume, and so in order to calculate a finite amount of work, you would need to solve an integral like this. Recall from our last discussion that work is a path function. It depends on more than just the values VI and VF in this integral. It also depends upon how the external pressure changes with respect to the volume. In some cases, it's constant. In other cases, it won't be constant. Okay? Those correspond to different paths, and the amount of work that's produced depends upon which path you take. I've essentially already discussed these 2 points here, so we'll move on to, here's a table showing you that there's multiple types of work. Like I said, we are going to be focusing almost exclusively on expansion type of work, but there's other types of work as well. Before we get into actually calculating work for different types of gas expansions, I need to discuss this topic of reversibility. So the term reversible or irreversible is used to describe certain types of paths. And the reversible path is one that can be reversed by an infinitesimal modification to whatever variable is involved in the change. So for example, if we're talking about a gas expansion, or let's do a compression instead. So let's go back to this picture here where we are going to compress the gas. Imagine that we're compressing the gas by adding drops of water to the top of the piston. Okay, so you increase the pressure ever so slightly. That's going to cause the gas to be compressed ever so slightly. Between each drop of water that you add to the top of the piston, you let the gas come into equilibrium with the external pressure. You could stop that compression by simply removing a drop of water. Okay? And then if you remove another drop of water, then the gas will start to reverse. The compression will turn into an expansion. Okay? And the drop of water is representative of an infinitesimally small change. So notice how that's part of the definition here. Okay? So a reversible compression or expansion is one that can be stopped and reversed by making infinitesimally small changes to the variable that you're modifying. Contrast that with an irreversible process. An irreversible process would be like taking a bucket of water, a whole bucket of water, and putting it on top of the piston. That would cause the gas to compress, and you couldn't stop that compression by simply removing one drop of water. It would continue to compress the gas. So reversible processes in principle, well, you know, if you were to try to design a reversible process, you'd have to carry out that process infinitesimally slowly, such that the system will always be in equilibrium with the surroundings throughout the path. As far as gas compressions go, that would mean that the external pressure equals the gas pressure plus or minus some infinitesimally small change in pressure, which you can basically ignore and state that the external pressure is approximately equal to the gas pressure. For irreversible processes, the external pressure does not equal the system pressure. Okay, they're distinct from one another. Essentially, all real processes, even our drop of water example, would in fact be irreversible. However, you can mimic the reversible process by carrying out a series of irreversible processes very slowly. One comment about reversible processes that makes them important is that they involve either a maximum amount of work or a minimum amount of work. In the case of a gas expansion, one derives work from the expanding gas, typically. And so the reversible process, the really, really slow process, represents the maximum magnitude of work that you can generate from that gas expansion. All irreversible processes that involve the same expansion would generate less work than that, less magnitude of work. On the flip side of that, let's suppose you're trying to compress a gas. When you try to compress the gas, you have to put work, you have to exert, you have to do work on the system. Okay, so it costs you energy to make that gas compression occur. And the reversible work in that case is the minimum magnitude of work that you have to do to make the gas to compress. All other processes, all irreversible processes where you're compressing the gas by the same amount, would involve a larger magnitude of work on your part in order to get the gas to compress. So the reversible process is kind of like this important limit, this important theoretical limit between, where you can calculate the maximum work you can get or the maximum work that you have to do. Or I should say the minimum work that you have to do. Well, in this problem, we are going to be doing a number of gas expansions, and we're going to be exploring the formulas that we need in order to calculate them. And so what you want to be able to do is to know what formula do I need to use to calculate work under different conditions, right? Because work's a path function, and you have to be able to calculate the work for different paths. And what I'm going to show you in this example is the how you derive the formulas for the work. So in part A, we're considering a free gas expansion, and then what a free gas expansion involves, an expansion where the external pressure is equal to 0. So that's what we mean by a free expansion. Okay. So in this case, the work, I'll use the infinitesimal version. The work is just going to be 0 in that case. Okay, so there's no work involved when you expand against a external pressure of 0. For part B, we're considering an isochoric process. And in an isochoric process, the volume change is 0. By definition. And so again, we're going to get that ultimately the work equals 0. So an isochoric, there's no such thing as an isochoric gas expansion. That would be a contradiction in terms. Part C. Here we're considering an irreversible expansion where the external pressure is a constant. Okay, so we're told that the external pressure is constant. So when we go to calculate the work, so here was our infinitesimal definition of PV work. In order to integrate this, in this case, and we would integrate it from the initial volume to the final volume. In this case, the external pressure comes outside of the integral because it's a constant. This is a very easy integral to solve. We get VF minus VI, and that's often written simply like this, as a delta V. So this is the formula that you would use when you're expanding or being compressed by a constant external pressure. Let's look at the case for a reversible isothermal gas expansion. And we're going to assume a perfect gas. So for the case of a reversible expansion, the external pressure is approximately equal to the gas pressure. So that's our reversible condition. Now, we're also being told that this involves a perfect gas, and so we can write this as nRT over V. Notice that the pressure is a function of the volume. And then we're also told that temperature is a constant, and so that's going to help us solve the integral. So we're going to set up our work integral. In this case, we've got minus nRT over V dV. We're going to integrate both sides. Okay. For an isothermal case, the nRT is constant, and so that comes outside of the integral. So I'm going to write isothermal next to this. So we use that adjective to simplify the integral. If it was not an isothermal process, we couldn't have done this. Now we have to solve that integral. So we're going to get that the work equals minus nRT, and then this integral is the natural log of VF over VI. And so this formula may be used when you have a reversible gas expansion under isothermal conditions, and the gas can be assumed to be an ideal gas. In part E, this time the external pressure, it's reversible, so it's still equal to the gas pressure, but now it's no longer an ideal gas. Now the external pressure is equal to the van der Waals pressure, which is nRT over V minus NB minus N squared A squared over V squared. And so now we've got to do an integral involving this external pressure. So it's going to be work equals minus the integral of P external dV. And we need to plug in, these terms here, nRT over V minus NB dV. We'll have another integral, I guess it'll be minus N squared A squared over dV V squared. Right, there's two terms now. We can do these, there should be a minus sign right there. So we can do these two integrals. So we're going to get minus nRT natural log of VF minus NB for the first integral, like that. And then for this one, it's going to be, I believe, this integral here is going to be minus 1 over V squared. Sorry, 1 over V. That's just the integral part. So the minus signs are going to cancel. We're going to get plus n squared A squared over, or times the quantity 1 over Vf minus 1 over Vi, like that. So you see, when you take into account the real qualities of the gas, the formula for the work gets more complicated. But in principle, it's calculated in the same way. On this slide here, what I'm showing you is a graphics. Well, on the next couple slides, I'm going to show you some graphics that go along with the calculations that we've done. So these diagrams that we're looking at, these are called indicator diagrams. And this one here corresponds to the case where we expand irreversibly against a constant external pressure. And so what's being shown here is a graphical representation of the work that's being generated. We're plotting pressure as a function of volume. Okay, and so in this case we have a constant external pressure, and then the volume is changing from some initial volume to some final volume. The area underneath the external pressure curve represents the work, right? We've got this expression here for the work. It's an integral, and as you learned in calculus, the integral, the definite integral, is a mathematical representation of the area underneath the curve. And so for the case of the irreversible gas expansion, the curve is just a constant, so it's a constant height, and then you have this width here. You can just interpret for the irreversible gas expansion, the work is the area of a rectangle. For the reversible gas expansion, under isothermal conditions, the external pressure follows the gas pressure. It's one of those hyperbolas, one of those isotherms that we've looked at previously. And so here we're calculating the area beneath this curve all the way down to the axis. Notice it's the reversible work plus the area beneath the isotherm. And so in this case, when the gas expands reversibly, we generate the maximum possible work that you can generate in that gas expansion. Here is just a summary of the key formulas that we've looked at, the ones that are most important. You definitely need to know all of these formulas, and it's not a bad idea to know how to derive them, frankly. So this is just a summary of what we've done. Here we are being asked to do a calculation of work, PV work, for a reaction involving iron and hydrochloric acid. And so let's switch over here. We've got iron, presumably as a solid, reacting with aqueous hydrochloric acid to give us some hydrogen gas and some aqueous iron chloride, iron 2 chloride, I should say. And so they want to know how much work is being produced when 50 grams of this iron produces this much hydrogen. And there's two cases. For the first case, when the volume is fixed. Well, that's an isochoric process. And as we've discussed previously, in that case, you can't do any expansion work, so the work is 0. For part B here, when we've got an open beaker, we're open to the atmosphere. and the atmosphere can be regarded as having a constant pressure, and so this is the case where P external equals a constant. And so in this case, the work involved is going to be equal to minus that external pressure times whatever the change in the volume is. And we'll assume that it goes from 0 volume to whatever the volume of hydrogen gas that is produced. And so really this will be minus P external. Since we're ignoring the initial volume, it'll be just simply VF. And in this case, we're going to just assume the ideal gas law holds. This will be, we can write the volume using the ideal gas as nRT over P, which will also be equal to the external pressure. Those cancel out, and we get minus the number of moles of hydrogen gas produced times R times T. So this is going to be a stoichiometry problem. We're going to convert, we need the number of moles of hydrogen. Notice it's 1 to 1, the stoichiometric coefficients, and so the number of moles of hydrogen the number of moles of iron consumed is going to be equal to the number of moles of hydrogen produced. So since we've got 50 grams of hydrogen, or of iron, we'll divide that by 55.85 grams per mole. So that's the molar mass of hydrogen. Sorry, the molar mass of iron. And so this is going to give us the number of moles of hydrogen produced. We'll take that times the gas constant, times the temperature. We're at 25 degrees Celsius, so that's going to be 298 Kelvin. And so this will give us our answer. So I'm getting minus, I'm going to convert it to kilojoules, 2.2 kilojoules is what I'm getting from this calculation. I will leave this second part involving the electrolysis of water to you as an example. It's going to be slightly more complicated because you're producing both hydrogen and oxygen gas, and you've got to take into account the expansion of both of them. But that's really just a stoichiometry problem, and so I'll just leave that one to you guys. Here is a different problem. So this is going to require one of those other formulas. In this problem, we are going to calculate the work involved when 1 mole of argon gas expands reversibly and isothermally. And so that involves a different formula for the work. It involves this formula. So we need the number of moles of gas, gas constant, temperature in Kelvin. Notice it has to be an isothermal problem. If it's not isothermal, that doesn't work. And then it's the natural log of the ratio of the two volumes. Okay, so we've got 1 mole of gas, 8.314 joules per mole Kelvin for the gas constant. Natural log ratio of the two volumes. The final volume is 30 liters and the initial volume is 10. So we'll do this calculation. And I'm getting minus 9.1 joules from that. Oh, no, scratch that. I forgot the temperature. I thought that was a little small. moles, 8.314 joules per mole Kelvin. We're at 20 degrees Celsius, so that would be 293 Kelvin. And then the ratio. Try that again. Looks like I just need to multiply by 293, my previous answer. So I'm getting minus 2.7 kilojoules out of that calculation. That's better. Notice the minus sign. The minus sign is due to the fact that the gas is expanding, and so the gas is doing work on the surroundings, and so the gas will lose energy as it expands. Well, in the next couple slides, I'm going to talk a little bit about heating. So we've talked about some work calculations, and you definitely need to practice all of those. That'll be one of the main things you need to do in the homework exercises. Next, we're going to turn to heating, right? There's two parts of the first law. There's work, and then there's also heat. So we're going to talk a little bit about heating next. Specifically, the path where we're considering isochoric heating, so heat at constant volume. In that case, when you have isochoric heating, the change in internal energy is simply equal to the isochoric heat, because there's no work possible. If there's no non-PV work and there's no change in the volume, that means the work is zero, and as a consequence of that, delta U equals the isochoric heat. Here's how you calculate the change in the internal energy for a constant volume process. So here's the definition that we're going to be working with. The infinitesimal change in the internal energy is equal to this heat capacity at constant volume times delta T. So we're basically assuming that internal energy is a function of temperature, and that here's how the exact differential of du can be calculated from a change in temperature. And to get to the finite version of this internal energy calculation, you need to integrate both sides of the equation. So du is a state function, and so that just gives you a delta U. In general, however, the heat capacity is a function of temperature, and so in general you will have to do an integral over the heat capacity from the initial temperature to the final temperature. Okay, and the slide that I have here is an illustration showing the internal energy increases with temperature. As you raise the temperature, the internal energy increases, and the heat capacity, this CV term, it's related to the slope that's tangent to the internal energy curve versus temperature. And so at the two different temperatures here, you have different slopes. That indicates that you need to do an integral over the heat capacity. Formally, the heat capacity is defined as a partial derivative of the internal energy with respect to temperature when the volume is constant. So that's what this notation means. It's the change in the internal energy with respect to a change in temperature when the volume is held constant. This notation here, this is called partial derivative notation. And in one of the upcoming sections, we're going to talk about partial derivatives in a lot more detail. But for now, we'll just take it as it is. This is the definition of the heat capacity at constant volume, or the isochoric heat capacity. It has units of joules per Kelvin. So internal energy is measured in joules, temperature is measured in Kelvin, so that's why it's joules per Kelvin. This is a extensive state function, so the heat capacity at constant volume is a property of the system. And because it's extensive, that means that the value, the numerical value of the heat capacity depends upon the size of the system. So if you double the size of the system, you would expect the isochoric heat capacity to double as well. We often talk about the molar heat capacity, that is the heat capacity per mole. So dividing this quantity by the number of moles gives us this molar isochoric heat capacity. You can also divide by the mass of your sample, and that would give you the specific heat capacity here, represented by this S, which would be in units of joules per Kelvin per gram. These are both intensive versions of the isochoric heat capacity. And so the heat capacity is related to the molar heat capacity by multiplying by the number of moles. It's related to the specific heat capacity by multiplying by the mass of your sample. Different substances have different molar heat capacities. So heat capacity is the unique property of whatever system you're considering. This slide here illustrates that the internal energy is a function of temperature, but in general it's also a function of volume, for example, right? And so it's showing us that this surface represents the internal energy. Here, if you walk along the temperature axis, that's how the internal energy changes with respect to temperature. You could also walk along the volume axis, and you can see how the internal energy changes with respect to volume. Then that partial derivative notation, what it means is that you want to assess, or this term, what it does is it quantifies how does the function u change as you change temperature while you keep the volume constant. Okay, so as you walk along this straight line where volume is not changing, you ask yourself, how does the internal energy change as the temperature increases? So it's equal to the slope in that direction. Note that if you changed your direction, the value of the slope would change, right? It has one slope along this direction, but it would have a different slope if you walked along the volume axis, keeping temperature constant. That's the point of partial derivatives, is to quantify the direction, the change with respect to a specific direction. And we'll talk about that in more details in a later section. For now, we are going to work a few heat capacity problems. And so in this one, what we're being asked to do is to derive a formula for delta U for a system where the heat capacity is given by this polynomial. And so here we're in the situation where, du is equal to CV dt. And to deal with the molar part, I'm going to change this to NCVM. So now we've got the molar heat capacity in there. And in order to calculate the finite change in U, I need to integrate NCVM dt. Now in this case, the molar heat capacity is not a constant, it's a polynomial, and so I have to do this integral. So the number of moles can come out, and then what I'm going to do is substitute in the polynomial here. So it's going to be a plus b times t plus ct squared dt. These types of integrals are not that tricky to do. So I'm going to wind up with a tf minus ti plus b over 2 tf squared minus ti squared. And then the third term is going to be c over 3 tf cubed minus ti cubed. All of that times the number of moles. Here we're being asked to calculate the heat capacity and delta U for heating a perfect monatomic gas under constant volume conditions. And so here we need to go back to actually that kinetic molecular theory where we had this relationship. This was a formula that we looked at previously where D refers to the number of kinetic degrees of freedom that we're dealing with, right? We arrived at this using the equipartition theorem. For a monatomic ideal gas, D is equal to 3. How do we calculate the heat capacity when we know the internal energy? We use the definition. We want to calculate the first derivative of U with respect to T, keeping volume fixed. That's easy to do in this problem because U does not depend upon volume for the ideal gas. And so we just need to calculate a regular derivative, an ordinary derivative of U with respect to T. And that's pretty easy in this case. We simply get 3/2 NR. So there's the heat capacity. Now they want us to calculate delta U for heating, for isochoric heating. In this case, du equals CV dt. In this case, the CV is a constant. And so to get delta U, we're simply going to have CV delta T. And so the result will be 3/2 NR delta T. So this would be the formula that we use for isochoric heating of a monoatomic ideal gas. If we had a diatomic gas, D would have been a different number. It would have been 5. For a polyatomic ideal gas, D would have been 6. Let's see, here we're being asked to calculate the heat supplied by a 55-watt electric heater that's immersed in a gas contained by a rigid adiabatic vessel for 120 seconds. And then the problem goes on. If the gas temperature rose by 5.5 degrees Celsius, calculate the heat capacity of the sample. Really, this is mostly just knowing that what the units of watts are. So a watt is a joule per second. So the heat involved would be 55 joules per second times 120 seconds. And that's going to be equal to the heat. So I'm getting 6.6 kilojoules. Now they want us to calculate the heat capacity. What we'll do is we'll say that the heat involved, because this is a for an isochoric problem, for isochoric conditions, heat equals delta U. Okay, and that for a gas being heated equals CV delta T. So then we can calculate CV by taking Q divided by delta T. All right, so that's going to be the 6.6 kilojoules divided by 5.5. And what I'll point out here is that delta T in degrees Celsius numerically equals delta T in degrees Kelvin. And that's because we're talking about a change in temperature and not an absolute temperature. So I'm getting 1200 joules per Kelvin for the heat capacity for this particular sample of gas. Well, I'm going to go ahead and stop this video here, and we'll talk about the next topic involving enthalpy in the next one.